Hello students, this is the third lecture of moment of inertia. In this lecture I am going to discuss about the moment of inertia of laminas of different shapes. So first I am going to find out the moment of inertia for a rectangular lamina. So I am taking first a rectangular lamina. So here I am considering a plain rectangular lamina which is having width B and depth D. Width B and depth D. So from the midpoint of the vertical side of this rectangular lamina or from the depth, I am considering an axis x axis which is passing through the midpoint of this vertical side of this rectangular lamina or the midpoint of this depth of the this rectangular lamina. Again I am considering one more axis yy, which is passing through the midpoint of this width of this rectangular lamina or the horizontal side of this rectangular lamina. So I can say the axis xx and axis yy are intersecting at a point, and that point I am considering as the centroid of this rectangular lamina, and the centroid is denoted by G. Now I can say the centroid lies at the midpoint of the width as well as the depth of this rectangular lamina. Now I am considering one elemental component or an elemental strip, rectangular strip in this plain rectangular lamina which is having depth dy, and the distance of this rectangular lamina from the axis xx is y. So the area of this rectangular lamina, the area of this elemental component will be dy into b. So we can write here the area of this elemental component will be dy into b. So this is the area of this elemental component. Now if I am taking the moment of inertia of this elemental component, about axis xx, so it will be the moment of inertia of this elemental component will be, see, if I am considering the area of this elemental component is dA, so it will be dA into y square. dA into y square. Now the dA, the area of this elemental component, I already found. The area of this elemental component is dy into b. So if I write in place of dA dy into b, so it will be dy into b into y square. So it will be b y square dy. So this is the moment of inertia of the elemental component about axis xx. And now if we want to find out the moment of inertia of the entire lamina, then it will be moment of inertia of entire lamina about axis xx. So it will be summation of, I already told you about the moment of inertia of the entire lamina in previous lecture. So it will be summation of this one b y square dy, by square dy. So it will be, we can write here as the integral of minus d by 2 to plus d by 2 b y square dy. So if we simplify this, we will get b y cube by 3 to d by 2 plus d by 2 minus d by 2. The simplification will be b dq by 24 plus dq by 24. So it will be b dq by 12. So this is the moment of inertia of the entire rectangular lamina about axis xx. We can write here as Ixx equal to bdq by 12. Similarly, if we want to find out the moment of inertia of the entire lamina about axis yy, so it will be the moment of inertia of entire lamina about axis y. So it will be d bq by 12. We can write it as I y also. So this is the moment of inertia of entire rectangular lamina about axis xx, and the moment of inertia of entire rectangular lamina about axis yy will be this. If I am taking this rectangular lamina as A, B, C, D. So if we want to find out the moment of inertia of this entire lamina about the face or about the bottom face of this rectangular lamina, the bottom face we are taking as face AB. So if we are denoting this as I A B, this is the moment of inertia of this lamina, rectangular lamina about the bottom face AB. So it is IAB, that is we can find out the moment of inertia by the parallel axis theorem. So parallel axis theorem will be IAB equal to IXX plus AH square. This is the parallel axis theorem, and we already have the value of Ixx. It is B dq by 12 plus, we have Ixx b dq by 12 plus area, the area of this rectangular lamina, the width is B and the depth is D. So it is the area will be B into D. This is the area. Now H we have the distance between face AB to the axis XX. It is D by 2. So it will be D by 2 whole square. So it will be BDQ by 12 plus, it is BDQ by 4. So this will be BDQ by 3. So this is the moment of inertia of this rectangular lamina about the bottom face AB. Now again, if we want to find out the moment of inertia of lamina about face AD, about this face AD, so it will be IAD. IAD is the moment of inertia of lamina about face AD. It will be dBq by 3. These are the moment of inertia from parallel axis theorem. Now from perpendicular axis theorem. Perpendicular axis theorem. The moment of inertia from the perpendicular axis theorem will be the polar moment of inertia. The polar moment of inertia. So it is denoted by IP. So this polar moment of inertia is basically the inertia about the polar axis, and this polar axis is basically an axis which passes through the centroid of the lamina, and it is also perpendicular to it. So this is the polar moment of inertia, and this polar moment of inertia as per the perpendicular axis theorem, IP will be, this is I x x plus I y y. This is the polar moment of inertia. Now we have the Ixx, it is b dq by 12 plus we have Iyy dbq by 12. So this is the polar moment of inertia. Now if we have a rectangular lamina, we have a rectangular lamina which is having width capital B and depth capital D. This is the x axis, this is the y axis, this is the centroid G, and it is also having a rectangular hole, a rectangular lamina with a rectangular hole, and the width of this rectangular hole is small b and the depth of this rectangular hole is small d. So the moment of inertia of this rectangular lamina about the axis xx, the moment of inertia for this, it will be moment of inertia of bigger rectangle minus moment of inertia of smaller rectangle. Moment of inertia of entire lamina. So this will be, if we are denoting this by Ixx, so this is moment of inertia of this bigger lamina will be b dq by 12 minus b dq by 12. So this is the moment of inertia of this rectangular lamina which is having a rectangular hole. So this is the moment of inertia about the axis xx. Again we can find out the moment of inertia of this entire lamina about axis yy also. So this was all about the moment of inertia for a rectangular lamina. Similarly, we can find out the moment of inertia for some other different shape also. So in this category, I am taking a triangular section, a triangular shape or triangular section. See, I'm giving you only formulas for all other shapes, like triangle, circle, and other shapes. In this, for this triangular shape, I'm considering a triangle ABC, a triangle ABC, which is having centroid G, and the base of this triangle is B, and the height of this triangle is H. I'm considering one axis XX which is passing through the centroid G, and it is parallel to the base of this triangular section. So the moment of inertia of this triangular section about axis XX, this is IXX, so it will be BHQ by 36. This is the formula of this moment of inertia of this triangular shape about axis XX. So this is BHQ by 36. Now if we want to find out the moment of inertia of this triangular section about the base AB, so this is the IAB equal to BHQ by 12. So this is the formula of the moment of inertia for the triangular shape. Now third shape I'm taking as the circle or a circular section. Circular shape or circular section. So here I am taking a circle of diameter D. The diameter of the circle is D. G is the centroid of the circle, and I am considering axis XX and axis YY which is passing through the centroid G. So it is, if we want to find out the moment of inertia about axis XX and the moment of inertia about axis YY, so it will be say pi by 64 d to the power 4. So this is the moment of inertia of this circular section about axis XX and about axis YY. So this is pi by 64 into d to the power 4. Now the polar moment of inertia or the moment of inertia about axis ZZ or the axis which is passing through the axis which is perpendicular to the centroid G. So this is IZZ is according to perpendicular axis theorem. This is IXX plus IYY. We have IXX plus IYY for the circular section. So it is pi by 64 d to the power 4 plus pi by 64 d to the power 4. So it is pi by 32 d to the power 4. Now for hollow circular section, if we have a circular section, a hollow circular section which is having inner diameter, the inner diameter of this circular section is di, and the outer diameter of this circular section is do. This is the outer diameter and this is the inner diameter of this circular section. We have two axes, axis XX and axis YY, which is passing through the centroid G. Now the moment of inertia of this hollow circular section will be about axis XX and about axis YY. This is pi by 64 d outer to the power 4 minus d inner to the power of 4. This is the moment of inertia according to parallel axis theorem. Now the moment of inertia according to perpendicular axis theorem, IZZ. So it will be pi by 32 d O to the power 4 minus d I to the power of 4. For a semicircle, if we have a semicircle of diameter d or radius r. This is the y axis, and we have the centroid at the center of this plane area, and the axis passing through the centroid G, that is axis xx, and the axis y. The distance, if we are taking this as the base, so the radius of this, we are taking the radius of this semicircle as r, or the diameter of this circle is 2r or d, and the distance of this axis xx from the base of this semicircle is 4r by 3 pi. This is the standard. So we can find out the moment of inertia about the axis xx and about the axis y. So about the axis xx, the moment of inertia of this semicircle is 0.11 r to the power of 4, and this is the moment of inertia about the axis xx, and about the axis y, the moment of inertia will be pi r to the power 4 by 8. Now if we have a quarter circle, if we have the quarter circle, the radius of this quarter circle is, we are taking as r. We are taking centroid of this plane quarter circle in the middle of this area. We have axis xx and axis y also, and the distance of the axis xx from the base of this quarter circle is 4r by 3 pi. So the moment of inertia about axis xx or about the axis y will be 0.055 r to the power of 4. The next shape is the ellipse. In ellipse, I am taking an ellipse having two radius. This radius as A, and this one, another one as B. The axis xx and the axis y. This is the centroid of this plane area. Now if we want to find out the Ixx, or the moment of inertia of this lamina about the axis xx, so it will be pi a b q by 4, and about the axis y it will be pi b a q by 4. So this is about the ellipse. Thanks for watching the video, and subscribe the channel for more lectures.